Good morning. It's good to see you all. I mean, it's great to have a local conference here in Sydney and not needing to fly anywhere and just grab your car and drive. It has been a while. You know, we haven't had a local student-run conference here. And, you know, we are always about supporting any local con, especially student one at SECtalk. So a round of applause for the organizers for making that happen. Now, my name is Pedram, and just briefly, just a few years ago, I started a new adventure in my career, and that is to start SEC team. We have a security game that will give a player a score by fixing a security bug. Now, I started this game or designed this game out of the necessity. A huge gap that we have between security industry and a software engineering industry, hacking versus building, and reporting security bugs, lots of them to the enterprises, and seeing, well, as long as I point to a problem, that problem may not go anywhere, and we may see the problem coming back because perhaps we don't have really good directions around how a security issue, especially on the software side, need to be addressed. Now, I'm not here to give you any marketing of my company. The whole thing is actually open to the community, so you can go and give it a try. This is just for us, hopefully, seeing more people be encouraged on a defense. And defense is not boring. It's very rewarding. It can be challenging. And if you like CTF, think about it as like a not capture the flag, more like a fix the flag to get your score. And boy or girls, it's more challenging. It's a lot harder. Well, today here, I'm going to talk about Web3. Now, I'm taking a very objective approach to Web3. You know, some people may like it, some people may hate it. You know, as a hacker, you just look at different computer systems, especially the ones that are so popular that being target of the security attacks, and in particular, the whole crypto industry has been target, and still today, of major incidents. So I think it's something that, as someone who is quite curious to figure out what is going on, we can look at it and find out what is the problem, and if there is anything we can do to make it better. Obviously, finding security issues in this ecosystem is the one side of a thing, but finding better ways to fix those is another challenge. How many people here are already familiar with Web3? And how many people have done any programming in Web3 world? Yeah? That's great. Okay, so let me start by a quick crash course introduction to this whole Web3 thing. First of all, it's scary. It's not a good introduction. Now, I'm going to give you a lot of analogy from non-Web3 world to the Web3 world. So imagine a world where adversaries could access any source code, even the code that is written by banks and enterprises. They'll just open out. Imagine it's a huge GitHub repository of every single code. So they can download the code, they can run the code. They can actually run the code with the real data and just to see how the system actually works in the local. Imagine you have a local VM on your machine and you have a code from one of the banks running there, and you can actually see the full transaction that goes to that bank and just run it against your code just to make sure everything is set up correctly. You can review the code. So if you are into code review, you can find bugs, exploit in that code, and you can build the exploit, or an adversary can build the exploit. And guess what? You can even test if the exploit works, and if it works, you can launch it against a production environment. Sounds scary? Or not? It's the usual thing. Well, welcome to the smart contract world, where the return of investment on doing attacks is pretty high. If I want to compare it with Web 2, like normal internet, and if some of you may have been familiar with some of the stages that an adversary will go through to compromise a target, I try to map each of them to different steps. So reconnaissance being when the adversary try to make him or herself familiar with the target. In a Web2 world, if adversary want to target an enterprise, well, they don't have a source code, unless an employee of that company leaks it out, like a recent incident with GTA. Otherwise, you don't have a source code. So you need to kind of black box hammering it. And I'm not talking about phishing attacks either. I'm talking about targeting their API or their servers. Web3, you have the source code. Initial access, if an adversary want to try it, is going to be against the production environment. In Web3, you can run it locally, test environment. In terms of execution of attack, well, in Web3, everything can be scripted. And guess what? An adversary can remain fully anonymous. This is the whole promise of Web3 or blockchain. So if you agree with me, the return of investment of attacking a Web3 is pretty damn high. And hence, we have a lot of attacks these days happening on these environments. OK, so let me go through a few terminologies here. This would be necessary for us for the rest of the talk. So today, I'm going to talk about one of the most simple security bugs. Sometimes I will change the word bug to vulnerability or defect. I'm referring to them as the same thing. And then we're going to see how to exploit this bug. And we're going to, of course, end this talk by possible ways that we can fix the bug. And we're actually going to see the limitation of this unfortunate environment that we can't really apply the best practices to fix it. So a smart contract, perhaps the term you have to think about it, is just a program, just any code that you run. But this program runs in a different virtual machine. You have run virtual machines, so it's not so different from there. The program will be compiled to the bytecodes. So there are the instructions, and those instructions will get executed in that virtual machine. So it's not a separate box. It's actually VM. Now, you heard about Ethereum as perhaps a cryptocurrency, but Ethereum that I'm going to refer here is this. Think about a Bitcoin plus a state machine. Anytime, if you remember from your computer science course, when we deal with a state machine, that means there's a system that we can write program for. That is like the foundation of any computer system. When you have states, you can have different events, and you can go from one state to another state, input, output, so you can have a thing that runs, a work. EVM, I mentioned, this is a name for that virtual machine. So Ethereum virtual machine. The difference between this virtual machine with your other virtual machines that you may run as part of a VirtualBox or VMware player is that everything that is executed in this virtual machine is across a distributed network. And that distributed network, guess what? Is a blockchain, which enforces some rules. Now, perhaps these things, as I go through, make more sense. So, and the blockchain that is that distributed network of these virtual machines can communicate to each other. So it's not a single VM run on your machine. Of course, we can simulate it. But in reality, you have a VM that runs, and whatever execution that it does, it puts on this network, and everyone else, all the other VMs can see it. And there are some rules enforced by blockchain, which is that distributed network, which will make this environment pretty safe for some executions. And lastly, like any other programming languages, when we want to write a program for a machine, we need a language. Of course, we can go and write things in assembly and instruction. Well, back in the days, that was the case. You could actually write instruction for the EVM, like many assembly instructions. Some of them, in a previous talk, may have you seen it. But Solidity is one of the many languages. It got its popularity. There are some other languages these days are coming in, but this one is pretty popular. And the syntax is quite similar to JavaScript. So let me give you a quick analogy. I'm sure most of you are familiar with web apps or web APIs here. So let's just see what is the difference between a web app and a smart contract. And by the way, feel free to stop me at any time and ask a question. I'm more than happy to answer it, because it may sound some of them confusing. It was for me when I started looking at this ecosystem. So, well, a web app is a program. in order to get executed, it needs to be compiled to the bytecode, right? Regardless of what language it is, PHP, Python, Ruby, Rust, whatever. Similar to the smart contracts, there's a compiler, we compile them to the bytecode, and that bytecode will be executed on the VM. Clear on that? Now, here is the first difference. Maybe sounds a bit crazy. Now, in web apps, let's say I want to make a transaction to my bank, my web, internet portal, and make a transfer from account A to B. It's just a HTTP request. You send it through, and then the response will come back, hey, you don't have enough fund, go and work more, and things like that, right? HTTP request normally over SSL, right, TLS, so it's secure, encrypted. If you want to do exact same thing in the smart contract world, it's like me standing in this room, and there are some virtual machines here, and there may be some of you of those virtual machines, and I will make an announcement, I want to make a transfer of this money from this account to that account. Can someone please be kind enough to make it happen? And then one of those kind nodes or VMs will pick that request and process it and give us the response. So it's nothing about point-to-point communication. It's more like you put the request in that distributed network, and one of those nodes will pick it up, process it for you. Now, back in the days, that was called mining. Now, the task of mining, this is actually, those nodes which do that, that process is called mining. Now, this has changed 2 weeks ago. I don't want to confuse you, but that's pretty much the whole process there. Another difference, which is interesting. Now, when you make a request to perform an action, perhaps add a user, delete a user, make a transaction, once you got the response, that's final. Either the money has been transferred or not. That's not the case in smart contract world. We have the concept of 99% final or finality of the requests. So the response is 99% correct. But there could be cases that everything get reverted and canceled. So this is, again, due to the safety and security of the blockchain, we have this design. So effectively, when I send a request, and one of the nodes pick that request and process it, I need to wait, on average, I'm just giving some number, 2 to 3 minutes. And after that 2 to 3 minutes, although I have the response, this response is final. Because there is other things going on with this distributed network that the nodes need to agree on all the transactions that are happening, things like that. And that request could get reverted, could get canceled. Now, in the blockchain network, I think it is around 10 minutes for a response to be final, well, 99% final. In Ethereum network, that is 2.5 minutes. Well, this number changes, especially after last week, the change that happened to the Ethereum. That has changed quite a lot. But in some other networks or blockchains, this number could be even smaller. Now, the other thing is the code. So the code that the developers they write for this word that's another interesting differentiation. In web apps, you build a program, we push it to the prod, and someone a security researcher comes out, hey, you have a, I don't know, CSEC bug, go and fix it. And then in a matter of like 2 hours, we jump in and we go there and fix the bug and push the patch, and that will be released to the prod. Because the code can be changed or mutable. In the smart contract world, the code cannot be changed. It's immutable. So meaning that once you push a code or the smart contract world, once that is compiled and pushed to the network, there's no way for us to change it. So if there is a bug in there, that's going to stay in the network forever. Am I pulling your legs? Or is it not? So how these vendors go and fix their security bugs when it is reported to them? Well, they effectively don't fix the bug. They redeploy a new code, a new program on the network, and then they point all the users to go and use this new code or new deployment of the code. There are some software design principles, software design patterns that you can use to easily do that. But behind the scene, that buggy code is always there on the network. That actually makes it very interesting for anyone who wants to get into the smart contract development or security, just to learn about all these mistakes that happen all the time, because those buggy codes are there, and you can go, and they're open source, and you can go actually see what was the bug, what was the problem. So the way that they are doing it here, they use a software design pattern that they point all the requests from that buggy code to a new code, which doesn't have the issue, but that old code is still there. And by the way, immutability is a great concept for security on web app world. So there are things we discussed to make it, the more immutable it is, the more, well, in some cases, better it is. Okay, let me go one layer deeper here. Give you a comparison between Ethereum virtual machine and a 64-bit machine. How many of you have done assembly here? Exploit development, of course. Yay. Come on, buffer overflow, stack overflow. Yeah, 64-bit machine, 32-bit machine, right? So it's going to be similar. Just give you a comparison again there. So in a 64-bit machine, we have the size of the register is, or how many registers do we have? 16 registers. In the EVM, I'm talking about we're dealing with a new machine, right? So that new machine has its own rule, has its own setup. There's no registers. I'll keep that in mind. Similar to x64, we have a stack, which is used for putting the arguments, passing the arguments to different functions, return calls, and all the other things. Exact same behavior in EVM. The storage, perhaps when I run a code, or it's going to be only on my machine, my hard drive. In EVM, the code of everything is on that network, so it's persistent across all what they call it full nodes. Now, I'm not going through detail of all the, so node is an implementation of one EVM. And there are different variations of them, but a node that is a full node, it has a perhaps copy of all the other smart contracts in that network. Execution, as I said, execution in the smart contract world happens on those nodes that are known as miners, and they get rewarded for the execution that they do. The size of the register in x64 is 64-bit. Now EVM, the word size there is 256-bit, which is interesting. Now, anyone remember Indianness? Not. I think I feel a bit lecturer here, but little endian or big endian, you know, so this is the way that the values are stored on the stack or in the memory of in x64. When we store hello world in the memory, it's actually being stored in a reverse way. So it's OLLEH. In a big endian, what you read is actually what is being stored on the memory. Why this is matter, we will see, because when I go a little bit to investigate one of the bugs, we will see it's a lot easier to investigate it here because it's big endian. All right, so let me just talk about cool stuff, where you can find those vulnerabilities. Well, the stack is huge. The smart contracts themselves, which we're going to dive in today, this is the code written by any blockchain, but they call it blockchain engineers or smart contract developers out there. So the possibility of writing a bug law is huge, and also the consequence of that is huge. But you can still find bugs, well, in a compiler. So Solidity is one of those compilers. And I think it's written in Golang, sorry, in Go. So, well, you can find a bug in a compiler, and that impacts all the other contracts. Or the EVM implementation. Geth is one EVM, so that virtual machine is implemented using a non-Web3 language. Well, that could be there. Or the protocol that is used by either the virtual machine or that distributed network. You know, for example, when we heard about Heartbleed and I don't know, those types of attack, which was a problem, some of them with the implementation or sometimes with the protocol itself, like why MD5 is bad and things like that. These are the bugs within the the protocol itself, well, imagine someone find a bug in the hashing algorithm used within this distributed network. The name of it is actually key check, or think of it like a SHA-3, so SHA-3. And of course, the blockchain itself. So Ethereum, there are other blockchains like layer 1, layer 2. I'm not confusing you guys anymore. But the stack is pretty huge. OK, so for us to get a good, quick intro into the smart contract security, I have picked the simplest and the easiest security vulnerability that we can investigate, which is super similar to the security bug that we have in a non-Web3 world. So layer 1 in the smart contract. And to introduce it, I'm going to start with one of the many incidents that happened in this world. So this was an incident happened in 2018 to a coin that is known as beauty coin or BEC. And someone stole that amount. I don't know what is that in English, but it looks to be quite large, in 2 transactions by exploiting an overflow vulnerability. Well, who was that someone? We don't know. And yeah, it's a sizable amount. Now, there's no one-to-one mapping of that beauty coin to the dollar value, but whatever it is large. What went wrong? Well, we are in a smart contract world. We can go and look at the source code, an actual request that made this exploit to happen. This is a snippet of that vulnerable function. Now, you don't really need to be a Solidity developer to understand that the syntax is very similar to JavaScript. And the other thing here, perhaps, is interesting for us is you can ignore pretty much the majority of the lines and only focus on line 3. So on line 3, we have a variable called amount, which is unsigned integer, or just an integer value, but the size of that integer is 256-bit. So we have a 64-bit int, we have a 32-bit, but in a smart contract, normally you deal with the 256-bit. And this amount is calculated by multiplying these 2 values, a counter and a value. Now, the problem of these 2 is, and this function is a public function. Anyone on the network can make a call to this. Now, as you could kind of imagine, if this value or this counter be bigger than the size of int, well, the result of this multiply is bigger than int 256, we have a rather classic bug happening right here, which is known as integer overflow. Now, how many of you are familiar with integer overflow? Like, heard about it? Oh, brilliant. That's great. But it's rather sad for me to see this bug happening to a machine, or EVM, or the whole Ethereum virtual machine the white paper of it was released around 2015. And integer overflow is a bug perhaps older than my dad. Like, it has been around since inception of computers, I think, or even not even computers. Sometimes when you go to when you look at the odometer of your car, when it goes to 99999, and then the next digit is 0000, is an integer overflow in the real world. So why we are still having it, that's a different discussion. But I just want to take a few steps back and really understand why we have integer overflow. Because there is one thing missing in EVM, and we shouldn't have integer overflow. So to really understand it, for a few minutes, I'm going to take a step out of the Web3 and go to a traditional Web2 world and to explore why integer overflow happened. Sounds good? You guys, hello? Yay? Yay! So registers, as we all know, they're just tiny memories in a CPU. And historically, even the calculators, those old school ones, we are using those registers for any arithmetic operations, plus, minus, multiply. When we're talking about tiny memory, that means we are limited in a memory size. And that means that the size of this register is limited. Now guess what? When we are dealing with a 64-bit machine, the laptop is in front of you, or the desktop's right there, that 64-bit is a hint that the size of that register is 64-bit in a CPU, which means there is a limit to what number we can store on that register. Now these two numbers that you see on the bottom, those are effectively the biggest number that you can store on a 32-bit system is this. So is 10 digit. The most significant digit is 4. And then we have the other number, which is a lot larger. That's the biggest number we can store on a 64-bit machine. But again, there is a limit. It's not like unlimited. So let's just ask some questions now. Now, suppose we have this pseudo code. It runs on a 32-bit machine. Now we have 3 variables, all in 32. There's a surcharge. There is a fee. So it's a 10-digit number starting with most significant digit of 2. And there is a total fee, which adds that fee to the surcharge. Questions. What will be the total fee when we are passing it to this function perform transaction? What do you think? We get some. Will it be a large positive value? That's a no. Large negative value? 2 people. 0? My computer gonna crash? It's going to be a large negative value. So suddenly we add 2 positive number, and we got that number out. In some, well, transaction or financial systems, a negative number means a refund. So instead of charging a customer, we may end up refunding them with that amount. So what is going on? So the people who mention it's negative, now my question to you is, but this number, let me go back, the surcharge is 2 something, 10 digit, is way smaller than a 32-bit system, which is 4 something. Why this number acts that way?
If it's assigned in, then the first number is the negative.
Beautiful, great. Because we need a way to store both negative and positive numbers. They're all concepts, but we need to formulate them in a computer world, right? So effectively, we don't use that 32-bit. We reserve 1 bit of that 32-bit to show that this number is positive or negative. So that's the first thing. So effectively, in a 32-bit system, if we are dealing with the positive and negative numbers, this is the range. 2, most significant bit. The least significant bit on a minus range is 8. This is an interesting one. The least significant bit on the positive range is 7. That sometimes causes a bug because they're different. The negative range is a bit more smaller. It's 8 and the other one 7. And similarly to the 64-bit, so that range will be divided by 2. But my second question is, why the heck the number wraps around? Couldn't we just say, okay, stop, this number is too big, I can't process that. We have lots of flags and things on the CPU saying that. But we can say, oh, overflow flag is set. This number is too large. I can't go beyond this. Why we just suddenly, the number goes the other way? This is to do with the way that microprocessors traditionally was built, and CPU is one of them. They follow modulus arithmetic. Now, I'm not going to confuse you. Modulus arithmetic is super simple because we're actually using it. Well, I'm actually using it a lot. When I go to a doctor, and the doctor would prescribe a medicine for me, and telling me, hey, Pedram, you need to take this medicine every 4 hours. And I go to a pharmacy. It's 9 p.m. So I already know that the next time I need to take this pill is 1 a.m. because 25 is an overflow condition in my brain. And then I just effectively 25 divide by 24, the remainder is 1. That's modulus arithmetic. Now, some of you may agree with me that that makes perfect sense in the context of time. Why did we use it in the context of microprocessors? Well, that's a design, that's a limitation, and we should follow on. So that big number that we had, the fee plus surcharge in a human world will result in this. But because this number is bigger than in 32, we need to divide that. The remainder is this number. And yeah, 2's complement, some of you may remember, that is actually means this negative number. So the reason we have overflow are two things. It's not just because we have a limited range. So firstly is, when we are using an untrusted data for doing any arithmetic, and we use that untrusted data for a field, a variable, or a data type that has a fixed range in 32, in 64, that's without doing any range check to making sure, hey, if this value, when I add it here or doing arithmetic, gonna go beyond the range, that's the first cause. The second cause, which causes this weird behavior, is this value wraps around. And the name of this is integer overflow. There are around 22 cases where integer overflow can happen in Solidity, or actually in many major programming languages. So pluses, minuses, multiply, division, plus, plus, minus, minus. Bitwise operations, so like shift left, because shift left increases the number. And casting, or changing the data type. So imagine we want to cast the data type from int64 to int32. And the number is stored in the int64, but then when we cast it to int32, we don't have enough bit to store it. Overflow also happens there. Now, but there is something a bit crazy here. It's because if I go back to the definition of where I started, I said we have int overflow because of the registers. But EVM does not have registers. So what is going on? Anyone can guess? We don't have registers, so we don't have fixed those tiny memories. Like EVM doesn't even have one, it just have a stack.
Is it because you do addition by doing subtraction? So you need to go from really, say, 0 minus 1 needs to go to that 2.
Yeah, that's right, but I'm just saying we don't have the limitation of the int32-bit system or int64-bit system because we don't even do the calculation on registers in EVM. Everything is virtualized.
Is it because the VMs are running on 64-bit based computers?
I wish that was the case. I wish that was the case. Not quite, yeah.
Is it just a pointer thing? So the pointer points to a particular address in memory, and the memory just overflows into something the pointer doesn't read?
Yeah, that was my assumption, yep. And what do you think? Do you think, what memory we're talking about, what is the size of that memory? Is it like allocated size in a memory? Yeah?
Yeah. Whatever memory is allocated for that program, I guess, and then sort of overflows into another part of the heap.
Yeah, we don't have heap. Like, that's the interesting part. But yeah, it's very similar to what you just described. This was actually got me curious that what is going on? Why do we have int overflow on a machine that does not even have a register? So effectively, memory should be limits of whatever arithmetic operation that I do. And guess what? I try to, like many of you as a hacker, try to reverse engineer everything because I actually couldn't find any guides that actually explain how this is being implemented. And well, I started my Kali machine and tried to point the GDB to a Solidity compiler and then the get, but that was like nightmare to just looking at figuring out where in memory my code is. I started Radar 2 or R2. They had a plugin for this, but that gave me sec fault. But just desperate not to do what to do, I find one. Can I have a demo now? Sharing my my thing. Well, I find an online IDE that relatively gives us some low-level view on, there we go, low-level view on the, on this, what is going on in the EVM. I will try to zoom in as much as you guys can see there, right. So anyone who wants to start programming in Solidity or blockchain world, most likely you're going to come across with a YouTube clip that talks about this IDE. So it's called Remix. It's a browser-based IDE that you can write a code. We're not going to use it for code. We're going to use it for reverse engineering. But everything that I said around nodes, compiling, deployment, they all happen in a browser, which makes things super simple to do. How do you find it? Well, you go just search for Remix IDE, and then you're going to bring this up. So right on the left, it already comes with some contracts, and I just show you an example contract here. It's not scary. It's very simple to understand. It's effectively, imagine there are some licensing things we have to put on the top. If we don't, the code will not compile. And here we just define what version of a compiler we want to use, which is a nice thing. And there we go. This is the whole code for this contract. Now, instead of class, we have contract. Just imagine it's like class something, right? And then we have some variables. And we have some functions. And these functions will get some parameters. And then we'll do something. Now, I believe this new contract, which I'm going to use for our experiment, we have license on the top. I have a range of compilers that I say, okay, these can be used to compile my code. And well, this contract is super simple. We have some variables, max sign, max unsigned, max, mean sign and mean unsigned. These are just helper variables for me because I want to reach to the edge of the range of this. This is nothing. We can just straight away look at one function here. So it's a function called arithmetic. It receives two variables, a and b, int 256. It will return int 256 value, effectively return a plus b. What is pure? Does anyone know? Functional programming? All right. Yes, doesn't have any side effects. It just adds this two value. Perfect. That means pure. Okay, so it doesn't really matter for our context. I was just a little bit was curious to know. But yeah, A plus B, right? So what we are going to do here is right on the, so this is where my code is, and that's the only code. We can ignore whatever other files you see here. Now, in the third icon here, which this is an icon for Solidity, here you can go and pick the compiler that you would like to compile this code for. So let's just pick version 6. What was the latest? Oh, yeah. Just give me a moment because this will need to fetch the bytecode for this code, for this compiler. And let me get this thing connected. Yep. It was interesting. Whatever I was doing was offline. Let me refresh this page. Can I get it? Can I go here? And let's just try this now. Okay. Just go back to version 6. It is now downloading the bytecode for this compiler to the browser. It's implemented in JavaScript. So now, once I press compile, this will compile this program. Why did you upgrade it? I want version 6. I don't want you to upgrade that. No upgrade, version 6. Compile. Why did you upgrade this to version? What is going on? Let's reload this. I'm trying to compile this with the version 6 of the Solidity compiler. Anytime I was pressing compile, it was picking the version 8 for some reason. Maybe because something in the URL here. I don't know. Let's open up the contract. Very slow. Refresh. Right. And then let's go to here. Pick version 6. Picker's resource. Nice, crashed. Overflow. Try again. All right, contract. I want to compile this contract, nice. And now I'm gonna go and pick version 6 and compile it. Please work. I don't like that.
In the Magma, maybe?
Maybe we just restrict it to one version, right? Oh, actually, yeah. Good point. Good point. That's why it's actually doing the right thing. I'm being dumb. Okay, let me just bring this back, and then I pick 610. I was choosing a really old version. Okay, 610. Can this work now? Oh yeah. 11. Failed to execute. Oi. Refresh. That's the problem of a browser-based ID. Don't know what is wrong. Maybe it's my Wi-Fi issue.
We can use the Wi-Fi here.
Yeah, sure. Which one is it?
Oh, you just guessed.
Yeah. Is it open? Do I need to sign in?
Just scroll up a bit, and then click here, attending a conference or event. Yeah.
Mm-hmm.
And the password is all capitals CTF 2022 exclamation mark. Excellent. Yeah.
Thank you.
Work. Cool to see done in the bottom right, and then yeah.
Beautiful. Thanks so much. Let's try again. Overflow. Well, I can see my code. Now I'm going to go and pick version 610. It's done. Aha! Finally compiled. So thanks so much. But there's one more step. You compile it. Now you need to deploy it on a network so we can play with it. Now you move to this tab here, and then you hit deploy. The UI is not very user-friendly, but here is actually what was deployed. So you can see all my functions, like this store function. This is my helper function. And these are my variables, which I had. So you can now see the value of them. Hopefully you can see in the back. I mean, there's a screen there. So this is like max sign. This is a maximum sign value you can store in a 256-bit type. Max unsigned is this, way larger than that. Okay, so let's go and try this unsigned arithmetic. But for now, I'm going to just add two numbers, 1, 2. So 1 plus 2. I'm going to get result 3. Works. So let's just now debug this and figure out what is going on. So from this bottom, these are like the list of all the transactions that I had. If you hit on debug, it's going to take you to this nice debugger, which since last time I played with it, they have upgraded it. But like many other debugger, you don't really have breakpoints in this debugger that I'm doing that, it's going to stop at one instructions. You kind of go back in time. So you perform an action, you hit debug, it takes you back in time, and you can review what happened to the stack, to the memory, to the variables. So at the moment, it takes me back in time where the values were passed around to this unsigned arithmetic function, 1 and 2. So like many other debugger, you have a step out, a step in, all the other things. Very similar. So there's a lot of things we don't care here. We can just close it. The values that was passed around, A is 1, B is 2. Now if I scroll down here, I can see the stack. That is pretty much what the stack is used for pretty much what this code is going to do. On top of the stack, so the first value is 2. So a stack is the last item put on the stack is the first item that will be removed, right? Same as none. And then we have 1. So the second argument that was passed. Now, what about the instructions? Instructions are up here. Since we don't have the convenience of registers, a stack is used pretty much for all the operations that needs to be done. For example, if we need to point to a memory address and follow the execution there, firstly we need to push that address on the stack, and then we will call another instruction, and that instruction will take the first value on the stack, pop the stack, and will go to that value. Or when we add two things, the result of the function will be again stored on the stack. Perhaps in 32 and 64, you normally store that in a RAX or EAX, but here everything stack is used. So the first instruction that I'm having here is push 0, 0. This effectively adds a buffer, like a 0 on top of the stack. If I scroll down here, you're going to see 0 being added on top of the stack. Very simple. Now, a new instruction, duplicate. If you remember from any buffer overflow exploitation, there is a lot of move instructions, like move this value from register to the memory, memory to the register to another register. We don't have move in EVM, but instead we have duplicate. Dup is effectively duplicate. The value that comes after it, like dup2, that means go and take the second value on the stack, so 0, 1, so not number 0, number 1, and put it on top of the stack. So just make a copy of that on top of the stack. It's effectively going to behave like move later. What it tries now to do, it prepares the stack for the add instruction, which will be called later. So, yeah. And if I go down to see the stack, you can see 2 is now on top of the stack. Now, the next instruction is duplicate 4. Now, if we look at the stack again here, 1, 2, 3, 4 is number 1. So once this instruction is called, I'm expecting to see 1 to come on top of the stack, you see? All right, now let's just move on, move up. We have add instructions. These add instructions will take the first 2 values from top of the stack, adds them, and put the result back again on top of the stack. Now I'm going to expect to see 3. And that's it. And then now from here on, it just does a bit of cleanup, popping and stuff like that, and then eventually comes back to the execution. OK, so there's a return instruction. That was pretty much adding 1 or 2. Now, how about instead of 1 and 2, this is unsigned arithmetic, I pass in maximum unsigned in 256 here, and add 1 to it. Let's see what's going to happen now. Now, what we expect to see as a result before I run this? My IDE going to crash, or what's going to happen? I wish it could crash, because that could stop a lot of security incidents. But what do we, so if I add 1 to this unsigned 256, what I'm going to get? Probably, sorry? Beautiful, yes, 0, because it's unsigned. We don't have negative range. As you can see, the result becomes suddenly 0. So that huge number plus 1, 0. What is going on? Let's debug this one. Now, A is this massive number. B is 1. The instructions are identical. Push 0, 0, duplicate 2, duplicate 4, add. And if you look at the stack, we see the notorious FFFFFF, so many of them. But let's continue on. So first, we create a buffer on top of the stack, add the first value, add the second value, and now when you add 1 to this, now it makes sense. Now it makes sense to me is because although we don't have registers, the stack has a range. And there is no, each entry of the stack, and because the stack is used for all the operations that that EVM does, now there is no way you can add 1 to a value that that is bigger than the size of this item on the stack. So now I could argue they could throw an exception saying that, hey, this is not possible, not getting there. This is because it's a virtual machine. It's not a limitation of the microprocessors. Most likely, and I'm being a bit, I haven't looked it up, it could be a default behavior. It wasn't even expected. But so now let's just think about, so we know now what is going on here. Let me go back to, where is my other slides? Did I lost my slides or they're shared somewhere else? Anyway, so before I start talking about how do we fix this, how do I share it? I minimize. Not this one. No, it's definitely is not here. Desktop too. This one. So just quick recap. So in x64, we had all the move and dest and source, copying from source to the destination. And this is equivalent of swapping 2 values, duplicate, push and pop. We exactly have those commands. And yeah, all these jump instructions are a lot more clear. You have a jump and jump with the destination. So you have a jump destination instruction. When you see a jump, that actually goes to the jump destination instruction. Very clear in there. OK, now let's now talk about how we fix this bug. What do you guys suggest to address integer overflow?
I was just going to say in terms of preventing overall, we kind of see either 2 things, I guess. One is like JSLint, which a JavaScript framework that just prevents you from doing dangerous things. Or like in Unreal Engine, we see blueprints and that sort of stuff. So I wasn't sure if that might be the next step, is that the compiler stop people writing dangerous code at all, and just say, these are your blocks, these are what you have to work with, or just not compiling anything the compiler sees as dangerous.
As dangerous. Let's just go a little bit more in depth there. What the compiler should check to stop people to introduce this bug. Any suggestions? It could be very straightforward. What do you guys think? How do we stop integer overflow? So was it? Yeah, go ahead.
Check the total is greater than like the number being added.
Yeah, so check if that when you, let's say just talk about adding 2 numbers. Let's check if that result is bigger than the range of that data type that we use to store it. Make sense? Is there any problem there?
If you're adding negatives, would that be a problem?
Let's just talk about positive range. Was it?
Don't you have to assume that the thing that you use in the check has a bigger data type that fits inside, and then you scale that up forever?
Scale it out. Now the problem is if you want to check that if you're adding 2 values, let's say the first value is the maximum range of that data type, and the second value is just 1, example that I went through. And then when we add these 2 numbers, the result overflows. So how do I check that? Because overflow already happened. So if I check later, I can't really say, hey, this is overflow because it's already become 0 in an example that you see. And 0 is in within the range, but due to overflow. Any other thoughts?
Maybe something, I don't know, maybe something modulo to make sure that there's enough sort of space for the second number out of it.
So the idea I'm hearing is there is a technique called upcasting. So effectively, when you want to add two numbers, let's say int 32 numbers, you do the calculation on int 64, because the result will definitely be smaller than you add two int 32 number, you're adding them together. The result is definitely smaller than int 64 because you have larger size. And then you can check if that result is within the range of int 32, and if so, you return. A question, what if the value is bigger than int 64? If it is a value coming from an untrusted source, that could possibly happen. Any other thoughts? By the way, that technique is being used quite a lot, upcasting, yeah. Any other thoughts?
Did you check like a carry bit, or have like an explicit function that's like be very clear that when you add it, it will overflow, otherwise like maybe panic or something?
Yeah, the carry bit is interesting, right? But how do we implement that? Because we don't really have that much of access, or we don't really have a register to check the carry flag. Any thoughts here?
I mean, you could have like a more complicated return frame on your stack that has the actual value and then some flags maybe and then another zero. Like instead of like the way.
No, perhaps the solution is quite straightforward. One of the techniques that we can use is known as precondition check or post-condition check to be more optimized. And to implement it is we need to look at a property of adding two numbers, and this goes to mathematics. When you add two numbers, a plus b equals to c, there are some invariants. There are things that regardless what a and b is, these invariants will always withhold. These properties will never change. Can someone think about any invariance or property of adding two numbers? Yep.
Hopefully they're not lower.
They are not?
Hopefully the total's higher than each of the numbers.
Exactly, right? That's like one of the invariants, right? So C is always bigger or equal to A or C, A or B. That by definition means adding. Now this property alone can help us to stop overflow, right? So when I add a number which is beyond the range of that data type, and then suddenly the value wraps around or becomes zero, that zero is smaller than one of those values. So we can simply use things like that. The other technique was upcasting, which I talked about. And the last technique is called using dynamically allocated data types. It's similar to upcasting, but there is no limit to them. Now, some of you may have heard about big integers, big decimals. We have almost in majority of the languages, Java, C#, JavaScript also supports that. Effectively, the memory is the limit of the range. And we hope the value that adversary puts in is not bigger than our, 64 gigabyte of memory. But problem, we don't have the support of it in Solidity or in the EVM. We don't have the concept of dynamically allocated data type. We kind of have something, custom data types, but it doesn't support it. So I would say one of the best practices in how to address overflow is not there for us even to use it. So we are limited into the first two. Now, second one already is not good because already is iffy whether we should be using it or not. So we limited to the first one. So this is an example of how we can potentially fix this bug. Suppose we need to create a function, like let's call it safe add. We're passing two values to it, a and b. We do the arithmetic, a plus b, but then we check if the result is, let's say, smaller. If the result is smaller than one of the values, we return false, otherwise we return true. Now, you can also say, I actually posed this question and someone on Reddit said, hey, you could actually throw an exception, which is a lot more explicit. Don't return false and true if it results into overflow, just throw an exception. So anyone who uses this function know that there is something wrong here. So rather than they have to check if it is true or false. A similar problem happened when we cast. As I said, from, let's say, from int 256, we want to turn that number to int 32. The only way for us to check it is effectively having two conditions, that if this number, if it is bigger or smaller than int 32, we immediately throw an exception. This require function is like, it will check for a condition. If this invariant or condition was not met, it will throw this error message after, and it stops the execution. In Solidity community, they, like up until version 0.8 of Solidity, we needed to use things like that. Safe add, safe cast. Sorry, safe add, not safe cast. And there was a very big discussion around whether or not this is something that we should rely on developers to do. What if someone doesn't even use this function? They're just new to whole development. They have no idea about integer overflow, and they start writing functions. So then they decided to implement this as part of the compiler. Now let me show that to you. If I go back here, by the way, stop me if I went over time. And instead of version 6.10, I compile this with version 0.8.0, which is the first version that by default we have the overflow check. Now I compile this, go to the deployment. So if this, the first one is the first time, this code here is deployed using version 0.6.10. This other one is compiled using version 0.8. Now just get the maximum unsigned value out and do the same arithmetic. Now, before just to do this arithmetic, let me just add two simples number. So add 1 to 2, result is 3. Now here's the interesting part. When we debug this, already in the instructions, if you look at here, it starts with what the bytecode that we saw, the assembly, the instructions that we saw for version 0.6, but there are some additions here. So these are the things that compiler find out that I'm doing some arithmetic and injected some additional instructions to my function. So similar to before, a duplicate 2, it takes 2 on top of the stack, and then duplicate 1. Duplicate 4, it takes 1 on top of the stack. But here, if you recall, we had the add instructions. But in this case, there is push this number. And if you remember, I mentioned in Solidity, in EVM, if you want to go to a different address, first you need to push that address to top of the stack. Now here is where that happened. Now, there's a lot of other instruction eventually it's going to go through. Now, this is a part that it will jump to a different function. Firstly, it will find out what is the range of my data size. So I just move a couple of instructions ahead. And at some point, we're going to see an interesting number showing up on our stack. So you can see there are quite a lot of instructions being just executed before doing any add. Now, right here, you see this push 32 with a massive FFFF value. This is where it figured out that I am using unsigned int 256, and this is the maximum value of that range. It pushes that on top of the stack. The next instruction is a subtract. It will gonna take that second argument out of this, and then it will do a comparison if this number is greater than what you have on top of the stack, the second argument. And if the result is 0, that means it's all good, and it's go ahead and now comes back. Now here, it jumped back to my original function. So we had like a massive detour, then there, find out what is the range of this data type, pushing the maximum range of data type to the stack, deducting the second argument from that, comparing with the first argument, and if it was all good, if the result was greater than 0, now we return back to my original function, which is now here we go. The add is just going to happen, and on top of this, like I have 1 and 2, and I'm going to get 3. Now, perhaps you are curious to know what will happen if I now give it the max unsigned int. So let's just give it the first value, that 1. Now, if I hit unsigned, I'm not going to get any result. So on the right-hand side, you can see that the transaction has been reverted, so it means it's canceled. Exception happened. Due to, where is it? Let me see, does it say what is the reason? Doesn't say anything. You just say it called my function. You just say it revert, but we can debug it. So just instructions are the same, just showing you the top of the stack. We have FF and 1, 0 was added. Now if we continue this on, now we go to the detour, go ahead. And now we're gonna see that FFFFF gonna show up. There we go. Now that went on top of the stack. Now I'm gonna subtract this with 1. The result is whatever E. I'm going to compare this with the other parameter. And since that is greater than that, it's gonna say, oh no, you can't. Now we're gonna jump to a different address. So now I'm not coming back to my own function. I'm going to some other address and says, naughty Pedram, this is revert. And it overflow. It stops the overflow to happen. Now I would say this is a good thing that we have in the compiler that enforces this check. So regardless if I'm being a clumsy dev and writing this code. There are 2 problems here. If you remember, I talked about 22 edge cases. Where is the other one? Did I again lose it? Where did I put it? There we go. Solidity version 0, at the time of we are talking, all the things under arithmetic overflow is covered by the Solidity version 0.8 and upward, but unfortunately the last 2, no. So still if we are doing any bitwise operation or any casting, overflow will happen and compiler will not help us. So that means still we need to be that responsible developer and know about how we can go and go after fixing this. And I think that was it. And one thing perhaps also would be interesting for you to know, anytime we do a transaction or any node that will take our request and process it, there is a cost of that, like any other cost for any cloud computing we do. And the cost in the EVM world is known as gas. So there's how much gas it requires to perform this transaction. Now, obviously, when we write a function or a contract, we want to make sure that it uses the least amount of gas. The more gas it uses, the more expensive it is to perform any transaction. By just injecting these additional instructions to our code, the gas that is actually used to perform a simple arithmetic has, when I was calculating, is like around 5 to 7% more than a normal arithmetic. Now, this could put off some of the contracts just because you just upgrade the version of your compiler, but you end up being gassed more for the same arithmetic function that you were doing before. And I think that was it. I hope you guys enjoyed it. Thank you.